overall goal is to link what we're talking about now with what we talked about the first month and a half of class or so. So fundamental theorem of calculus is the thing that does that. And what we talked about already is during that, if I want to express how much of something I have, I can talk about it being generated by accumulation. If I know a rate at which something's changing, so if I know the rate at which function f is changing, if I have one value of that function that I know, like so one like coordinate pair a comma f of a, if you're thinking graphically, or an xy point, or just at some point in time I knew a value of this function's dependent quantity, then all I have to do is take and add on to that. Then after that, what happens due to my rate of change function? So if I start at this point, whatever lowercase a is representative of, some parameter, some place where I knew the value of function f, and I let the rate function that corresponds to function f generate, so r sub f evaluated at miscellaneous points, multiplied by a little bit, so this is my MDX sort of expression. I let t take on all the values between a and, well, x in order to get x here. If I wanted a specific numerical value, if I wanted to know something like f of 7, I could say, oh, well, as long as I know something, it doesn't have to be larger than 7, smaller than 7 in reality, this a's size doesn't matter. But I could find the value of this by taking whatever starting value I had and then using a rate from a to 7. If 7 happened to be smaller than a, this would, end up taking away what happened because of the rate. So that the relative size doesn't actually matter. But the two ways that this is generally used is this way, to explain a function and how it's generated from its rate. So this is like our y final equals y initial plus MDX sort of equivalent, but with calculus to explain the fact that, well, I don't have one constant rate m that I use all the time. I have a function that describes constant rates that can change whenever it feels like it. Could be changing at all values. It could be constant, doesn't matter. We can express it in general this way, though. The other sort of way that the fundamental theorem of calculus is typically used is in a more numerical sense. And that's usually thinking about, like, well, how much accumulates between two fixed points? And so it's really just an algebraic rearrangement of this with more numbers put in, but usually you'll see it written as something like f of b minus f of a. The difference between two values of the dependent quantity of this function f depend on, well, what was the rate of change of this function between a and b? And what did it accumulate between a and b? Well, the rate of change of f, oops, and I'm squishing things together because talking and writing at the same time, but let me just fix this a little bit. R sub f of t times dt. So same sort of expression in the integrand, and all this is our MDX expression, but this is adding up all the changes between point A and point B, and so that tells us net change between, or net change on the interval A through B, whereas this gives us kind of a formula. It gives us a function rule. So this f of x equals, that's a way to define function f of x in terms of its rate of change in a starting point. So we get a sort of an alternate description for it, maybe different from what you're used to seeing, but it is a description of how to find values of f of x for any value of x. Just pop in a number there. But if you do start putting in numbers there, then you get something that looks more similar to this other half, and it's not like that's a bad thing. It's that these are just two different ways to describe the same relationship and ways that it can be used. And so, like I said, in general, you'll see two different halves to what's called the fundamental theorem of calculus. It's not that they're actually different rules, it's just that they're explaining the same relationship from two different viewpoints. All right, so let me clear this off. Actually, let me not. So thinking about this whole integral notation thing, let me just point out that if you understand what integral notation means, there are some of these that are, if you see an integral expression that's a numerical value, there's several of them that you probably could figure out without too much difficulty. So something, if I said something like 0 through 6, ooh, apparently I touched something. That's definitely not a 6. Not try to push me. I'll write this lower. 0 to 6, 4 times dt. Now if I said evaluate this, like, well, what on earth does that mean to do? So think about the meaning of this expression in terms of rates and accumulation. And what sort of rate we've got and what those sorts of rates do. Or think about what it could be the rate of change for and what this means. But remember that the expressions after these integral signs, you can think of them as indicating a rate of change of some other function. And this is our MDX sort of expression. So this 4 here, this is our rate of change. So the rate of change of something is a constant. It's the number 4. What sorts of functions have constant rates of change? One number throughout. Yeah, linear. Linear functions have a constant rate of change. All right, so we could think about, oh, well, this is talking about a linear function and how much net change there is in that linear function with rate 4, like $4 per gallon. How much gas do you use, or how much, $4 per gallon, how much does it cost you to buy, well, changing from buying 0 to buying 6 gallons of gas? Oh, well, $4 per gallon for 6 gallons, that's going to be $24. Now, the value of this expression is 24 because I've got a constant rate that accumulates over 6 units left to right. Notice that that would be the same if I had something like 2 through 8. Because it's a constant rate, it doesn't matter what interval I have specifically, just how long that interval is. That's visually speaking, if you're thinking of, oh, linear functions, I don't really know what linear function this is. It doesn't have to have started from 0, but just what I know about this is the net accumulation from wherever I'm looking here. It's like, oh, well, wherever this A is, let's say the A is 2. Lowercase a, that is. Starting at 2, whatever this is, and I'm increasing at a rate of 4, meaning no matter where I draw a little calculus triangle or how big I draw it, there would be a ratio of 4 to 1, changes in y to changes in x. It can be in any position and any size. That ratio is going to turn out to be 4. But if I change from an x value of 2 to an x value of 8, oh, well, I can just do one big calculus triangle because it's not really differentials when I'm talking about huge changes, but when I've got a constant rate of change, the size of my changes, as you remember from forever ago, doesn't really matter. It doesn't make it less exact because, oh, well, this is a change of 6, so I need a change of 6 times 4 here, or 24. And this doesn't mean that something about like buying, like, oh, it costs me $24 to get 8 gallons of gas or anything like that. This is just, if this were gas in dollars situation, this is the extra cost incurred by increasing the amount of gas I purchased from 2 to 8 gallons was $24. It's just that extra amount. So this is a net accumulation. It doesn't tell us total overall. Maybe there are some surcharges for using a debit card. Who knows what else there might have been on there. But in any case, there are some sorts of these integral expressions that we already know how to evaluate if you keep in mind what the meaning of them is. They look sort of intimidating because there's a lot of symbols in there, but just thinking something like, let me write down something like this. Now, I'm not going to put a f of x equals, so I don't have to worry about, I'm using x's in weird spots. But if it's something like this, I picked this function on purpose. I've got my mdx sort of expression, 2x dx. So my rate function, the rate of change of something or another, is 2x. And I want to know what that sort of rate accomplishes between 0 and 10. Now that's not a constant rate. When we're in the moment x equals 0, that would be a rate of 0. But at the moment I move away from 0, it's a small positive number, and it gets larger and larger as I progress towards 10 until when I'm near x equals 10, the moments around that area have rates of change nearly 20 y's per x. But we talked about this result last time. What sort of function, thinking backward, what function did we talk about that has this as its rate of change? Yeah, quadratic, x squared. We talked, this was our power rule. We went through this example, I think, actually the tail end of last week, Thursday, and then we went over it again during Tuesday this week. So there are lots of functions that actually have this same exact rate of change formula, but they're all the same steepness everywhere. They're all the same shape. They're all different parabolas. Just like there are a whole bunch of different lines that have a slope of 4, the only thing, like y equals 4x, y equals 4x plus 2, y equals 4x minus 3. The other parts aren't the changing parts, so they don't contribute to the rate of change. They're the constant parts. So they can have other constants, and it doesn't affect it. But if I want to know what happens because of this rate between x equals 0 and 10, all I have to do is come up with any function that has that rate. Doesn't have to be a specific one. And what happens to that? Because this function has that rate, so this or anything else, because of the rate of change, would have the same net change between x equals 0 and 10. Well, how much does f of x, this f of x, change between x equals 0 and x equals 10? Well, at x equals 0, it's equal to 0, and at x equals 10, I've got 100. So how much was that change? It increased by 100. So the answer to this is 100. Now, just as a side note, especially for those of you that might have had calculus before and like, wait, but what about the other number? Like, so if this had plus 17, all that would do is make both of those larger. But the change, which is what this is asking about, what's accomplished because of the rate, it's the same. It's still 100. Whether I came up with some other function that had the same rate or the one that I just made up because it's simplest and we happen to have talked about it. So that doesn't actually, it doesn't actually matter. If I want to know net change, I don't actually care about the y values individually. I just care about how different they are from one another, y final and y initial. Or notice that this is just, in terms of the expressions we had before, this is f of 10 minus f of 0, y final minus y initial. This is that part 2, not this part, the part 2 of like the more numerical sort of aspect to this. Now, let's get back to talking about finding rate of change functions so that not only can we do a mastery test eventually, but so that we can answer more things like this with different sorts of expressions here. Because this, I just picked that because that's one of the few that I was thinking maybe that would be recognizable. So this one. All right. So I'm going to skip over the proof actually for power rule, because if you want to see it, it's in your book. This is section 6.3, and it shows how we can devise this power rule that we talked about last time. So they show a x cubed worked out all the way. We did x squared and something with x cubed. It wasn't 4x cubed, it's 4/3 pi x cubed. it's a pseudo proof. It doesn't actually prove anything. It's just kind of like, look at the patterns. This should make sense as to how a power rule works. But the result of this is, if I have a function of the form x raised to the n power, where x is a variable and n here is used as a parameter representing some number. In fact, it can be any real number. These are called power functions. If it's a whole number, it's a monomial as an alternate term. But with any sort of power, just x raised to a numerical power, a variable raised to a number power, is called a power function. And its derivative, or its rate of change function, the function that describes the ratio between y and x changes, is given by this n x to the n minus 1. So we saw this in a couple of cases. The power gets lower. The power's lower in this rate of change function than in the original. And we gain a new coefficient that happens to be what the old power was. So just thinking of patterns in order to do this quickly. Now, we didn't talk about this one, but I think we can do this quickly. What if I have a function that is, so f of x equals c. So c isn't a variable here. X would be the variable. C would be representative of a constant, meaning the letter c is a parameter here. If I have f of x equals 4, or f of x equals 19, if f of x is a constant function, it has one y value throughout. What is its rate of change? What's the rate of change of y with respect to x if I have something like that? 0. Yeah. So think about, well, how much is y changing? Well, if y is always 7, or whatever number it is, it's not changing. What's the rate of change of f of x equals 7? It's 0. Or if you want to equate this to, we're just talking about linear function with a slope of 4, y equals 4x plus whatever you want. Y equals, or f of x equals 9, something like that. That's a linear function also. It's just slope 0, if you want to think about that. Its rate of change is 0 because it's, well, the y values aren't changing. So the rate of changes of y with respect to x is 0. Now we did talk about the concept of, well, what if I have a constant multiplied onto the front of some other function? These top two rules here are talking about a specific type of function, a power function, or a constant function, which you could pretend is power 0, and it would work out this way. That's just not really what's going on. 0 times x to the negative 1, I don't know. But if this is just describing a relationship between two functions, if I have one function that's a multiple of another, such as in class when we talked about 4/3 pi x cubed, that 4/3 pi ended up being something we could just factor out of that whole x plus h and x over h process. So that constant just has the effect of multiplying what otherwise would have been the rate of change function by that same exact constant. Or, what was the other thing that we had something else? Oh, I know we were talking about the tail end of Tuesday. If I had, we worked out quadratic derivatives or quadratic function rate of change, y equals x squared versus y equals 17x squared. That coefficient just multiplies on. If you're thinking graphing something, it makes it steeper by a factor of 17, which is that rate of change greater by a factor of 17, or whatever the number is. So if you multiply by a constant, if you have a coefficient that's multiplied onto a function or a term, all that does is scale up or scale down depending on the size of that constant, or even negate if it happens to be a negative number, the otherwise what would have been the rate of change had that constant not been there. So if I know how to find the derivative of, or the rate of change of g of x without a coefficient on it, if I throw a coefficient on it, call it a new thing f then, well, I just multiply on that same coefficient, that same constant multiple, onto the derivative. And that sounds kind of much more complex than it is. I'm going to go through a couple quick examples. But I did want to point out one rule, and this is what I said we're going to talk about more today. What if I combine different functions together? Adding, subtracting, multiplying, and dividing is what we're going to talk about today. So if I have something that's two separate functions, so maybe k of x equals 4x squared plus 9x, well, let me actually use that exact example, 4x squared plus 9x. Pause on this for a minute. You could probably see what the result is there, but I'm just going to use this blank screen, mostly blank. All right, so just using our trusty derivative rule, if I have f of x equals, oh no, I forgot what I said, 4x squared plus 8x, no, 9x, I'll do 9x, whatever it was. If I wanted to find the derivative of this, or the rate of change of function f, according to our rule, I'd need to do f of x plus h minus f of x all over h, and then let h become essentially 0. So imagining h to be 0 after we've done, as usual, a little bit of algebra so that it's not this tug of war between numerator and denominator both being essentially 0. So f of x plus h here, this first term is going to be kind of similar to what we worked on before. I'd have 4 times x plus h quantity squared, and then the rest of f of x plus h comes from substituting in x plus h in place of the variable x into the second term. So this is my f of x plus h. I'm just going to put big parentheses or brackets around it. Not in reality necessary, but oops. And then minus f of x, 4x squared plus 9x, all over h. So just thinking about, this is the expression that I want to clean up a little bit. You can maybe see, well, between the first and the second halves of this numerator, there's going to be, when I expand this, I'm going to be able to subtract out that from it. Or just rearranging a little bit, 4x plus h squared minus 4x squared. And then 9x plus h minus 9x. I just rearranged the numerator a little bit. Would you agree that that numerator is algebraically, oops, other than I put my squared in the wrong spot, algebraically equivalent to the first, that these two are the same? Just kind of writing the subtraction differently. I've got a positive, a negative, and a negative. Now I've got a positive and this negative with it. And then, oh, it's not the same right now. Plus, there we go. And then this positive and that negative with it. Now these are the same. And according to how we work with fractions, I've got 4x plus h squared minus 4x squared x squared all over h, and 9x plus h minus 9x all over h. Those two fractions with the same denominator, if I added them, would be the same as the one above. But this part right here, if you look at it, is exactly, well, if this part had a name, this would be how I'd find its rate of change. And if this part had a name, like maybe this is j and this is k, well, this part would be how I'd find its rate of change. So since I know how to find the rates of change of those two terms separately, there's no new magic introduced by having added those two terms together, or even if there was a subtraction between them. Again, no new magic would be added. I could just rearrange addition and subtraction and end up with two separate things. The gist of this is that the rate of change function for this function f is just the rate of change of its first term plus the rate of change of its second term. So when you have polynomials, you can, or multiple term expressions of any sort, you can just think about, worry about, what are we going to do, finding the rate of change of each individual term, each individual piece that's added and subtracted separately from the others. It doesn't want, the third term doesn't impact the first term's rate of change. They each have their own, and by adding and subtracting, this is not true with multiplying and dividing, with adding and subtracting, these all stay separate. The problem with multiplication and division is the distributive property. So those are a little bit more messy. But our rule then that we have is, back to this, oops, if I have this function k of x that can be defined as the sum of two other functions, all I have to do is find the rate of change of those two other functions and add them together. And this extends to like 3 and 4 and 5 terms, and however many you have. But again, terms are defined by sums or differences, which are just a -1 times. Sums are differences of pieces. So suppose I want to find the rate of change of a square root function. I want to point this out specifically because square roots are a fairly common thing to occur in functions, and although there are a variety of ways you could approach them, if you just kind of know this rule off the top of your head as a separate thing, it can make your life a little bit easier. So it also involves the simplification here, a different algebra simplification that you might not have thought about in a while, so I just want to bring that back to mind. In case you hadn't thought about rationalization in a while, and difference of squares patterns. So if f of x is the square root of x, its rate of change function can be defined this way. This is our general trusty rate of change format. So to work out what this comes down to in a more simplified form, we're going to use a technique of rationalizing the numerator. In algebra, college algebra, you typically did some weird things. Rationalize this denominator. You don't want to have square roots there. It's the same trick, but just we're going to do it to the numerator, because the numerator is where I have this messy thing that can't be simplified. So this r sub f of x, you see this, there's these two factors here. The one on the left, this is r sub f of x. The factor on the right here is a fraction that has the same expression on the top and bottom. It looks fairly horrible, but it is equivalent to 1 as long as the radical expressions are well defined. They're not weird imaginary things. So, or 0. I don't want 0 over 0. I want the top and the bottom to be the same. And if I multiply the numerators together, this is why this bizarre looking expression was chosen. The numerators of these two fractions are nearly the same. They're the same two pieces, but the first has a subtraction in it, the second has an addition in it. So just kind of like x plus 2, x minus 2, when you multiply it together, it's like x squared minus 4. The O and the I of FOIL cancel out. Same thing with this. If I multiply together these two numerators, it actually gets rid of the radical signs, because what I get is the first quantities squared, which is, well, x plus h's square root squared is going to be x plus h, assuming that I've got properly defined x's and h values that made sense in the first place. And then when I square square root of x, I get x. So the numerator of all of this is x plus h from squaring the first two terms, and x from squaring the second two terms. The cross terms from distributing cancel out. They're opposites of one another due to the plus and minus sign. But this numerator, you can see, this simplifies down to just h. And I can factor out that h and reduce it with the denominator. At which point, just like some of the other weird simplifying we were doing on Tuesday, if I cancel out this factor of h, so this numerator here would be just h, and the denominator has a factor of h. I didn't bother multiplying that out. I'm just going to cancel it anyway. So reduce out a factor of h from the numerator and denominator. All we're left with is this 1 over a couple of terms. Now they're not quite the same right now, but if I imagine that h is essentially 0 and that's gone, then what I've got in the denominator is essentially square root of x plus square root of x. They're almost the same, or 2 square roots of x. If h is essentially 0, these are essentially root x plus root x. So just like x plus x is 2x, square root x plus square root x is 2 square root x. So fun with algebra, and all the lovely things you did in college algebra and pre-calculus classes comes back to explain how this works, but here's the nice part. I don't want you to go through and do this all the time. If you notice this result, the derivative of square root of x as a shortcut, and this is listed actually on your list of derivative shortcut rules or rate of change function shortcut rules, just 1 over 2 times the square root of x. This can also be seen actually though as an example of using power rule. So power rule said that if I have x raised to a power, then its derivative has, okay, so I get a new lower exponent and a new coefficient. What power of x is equivalent to square root of x? 1/2, right? So if I think of this as x to the 1/2, then use power rule on that. I'd get a different form of the answer, but through algebra, we could rearrange it into exactly what we had before. According to power rule, I'd have 1/2 x to the 1 lower a power would be negative 1/2. And x to the negative 1/2 indicates a square root of x in the denominator multiplied by a factor of 1/2. That looks exactly like the same thing. So it's not actually a different function. Now this 1/2 power wasn't proven by that whole binomial expansion thing at all. As I said, we'll do a better proof for power rule later on. But this 1/2 x to the negative 1/2, you can use that as a derivative of square root of x. You can also use this, but square roots do crop up a lot. Cube roots are not the same as square roots. They're different fractional powers, but they have, you can do derivatives of those somewhat similarly. But square roots are, like I said, they're just fairly common. So just as a something to have in mind, if you see take a derivative of a square root, you can think either quickly power rule 1/2 power, or you can think of this just, 1 over 2 times the square root of x. So this is just a specific example of one specific power, but anything that can be written into power form, so that would include things like maybe 4 over 7x to the 5th. Oh, that's the same as 4/7 x to the negative 5th, a coefficient and a power of x. I know how to deal with coefficients, powers of x. I've got a rule for that. So between now and the end of spring break, you're going to, I hope, maybe get a chance to familiarize yourself with these rules. So that I know there's a lot of shortcut rules because I don't want you to have to do algebra to get through these all the time. But what I did want to point out, I posted a couple of different things on Canvas. One says like a rate of change check. And what it is, it's just a GC file that has some stuff pre-typed in it. But if you wanted to know if you've got the correct rate of change function using shortcuts, you can use GC or any graphing utility to compare what your result is to what you should have gotten if you used all of the algebra and the x plus h's. So what I mean by that is, let's see, GC, other window. This is just, I just downloaded this from Canvas. It's on the module 2, which I apologize, at some point in time yesterday I depublished module 2 and I don't know where it went, but it came back. Thank you, whoever it was that let me know that it was missing. But if I have, and I just put some text in here so you could see what I meant by all of this. If I have an exact accumulation function or something that I want to find a derivative or rate of change for, I can just type it in for f, and I can guess what its rate of change function is. So let's say f of x was, like I said before, like square root of x. Oops. Square root of x. And we came up with 1 over 2 times the square root of x. Why is this not? No. There we go. We came up with that as the rate function. Now, according to definition, to find the rate of change of function f, so this is all defined in here as f of x plus h minus f of x all over h is going to be a blue graph, and I want to compare it to my red graph. So I made up this function, or I was trying to come up with derivative rules, and I think using my shortcut that this is correct. Well, I know it's correct, but pretending that I'm checking my work here. Here's what it's supposed to come out to be. What I want to do is compare the graphs of these. And all this is I just made a slider that I can call H. But let me scroll up a little bit. So with the square root function, I can see, I didn't make like a moving graph or anything. With the square root function, I can see when H is smaller, my red graph, which was, the red graph was the guess. Oops, let me get this back to something. There we are. The red graph was the guess, and the blue is how it's supposed to turn out. So if H is extremely small, the red and the blue seem to be overlying one another. So that's a good sign. I mean, it doesn't prove that you're correct, but it's a pretty good sign that you're correct. Now, it doesn't have to be this function in particular. If I say, all right, well, so what if f of x is, let's see, what did I have before? Like 4x squared minus, or plus 9x, I think I had before. And we think that the derivative, the rate of change function, is supposed to be 8x plus 9. We would be correct, but you can check that. You don't have to do anything else down with the rest of this. Just, all right, let's see if red and blue come out the same. Yep, when H, you can see them separately, and when H gets smaller, it gets closer and closer to where that red one was until they're just over top of one another. So you can use this file just to kind of check your results. It's maybe especially important on more complex looking derivatives or ones where you're not sure if you understood the rule properly. You can double check using this method. So for instance, what I'm going to do, let's say that next thing I want to talk about, different sort of function. We've talked about power functions. We've talked about adding and subtracting them and having constant multiples. What if I have something that's not a power function, like 3 to the x power? That is not a power function. This is called an exponential function. And this is not my guess at what it looks like. But if I graph f of x, I'm going to graph f of x in black. And there's still a blue thing here. This blue is the rate of change, this exact rate of change function. So why is my, oh, I didn't have a y equals f of x, sorry. Y equals f of x. I'm going to make that black. There we go. So my black line here is y equals 3 to the x, f of x equals 3 to the x. And it's not exactly, like, it doesn't, this is the smallest h gets. It's not quite the same, but looking at this, like, well, what on earth would a rate of change function for 3 to the x look like? Well, visually, it looks kind of like 3 to the x, just not quite. And maybe I could make h smaller. It's not actually going to be exactly the same, but it's pretty close. Or something that I could say about it is, well, whatever the rate of change function is, it seems to be exponential also. It's the same sort of function. It's just not exactly 3 to the x. It's a little bit off. And in this case, it's y values are, you can see the derivative is the one that's on top here. The y values are a little bit above 3 to the x's y values. So let's take a look at some other exponential functions. Like, let's say 5 to the x. Does that do the same thing? Well, this is again with h very small. Well, 5 to the x, that's a little bit farther off, but again, it's the same sort of shape. The blue derivative curve, the blue rate curve, seems to be the same sort of function as 5 to the x's, but just, well, larger y values. Well, let's see if I have something like 2 to the x. When h is large, I've got my rate of change function is up above, but if you saw where that was, when I have 2 to the x, I've still got the same sort of shape, but when h is small, it's a little bit less than 2 to the x, a little bit smaller than. You can see the y-intercept, instead of being at 1, and looks to be like about 0.7 or something. So let me just show you one thing. E to the x. Now, e to the x, when h is large, when h is smaller, with e to the x, it seems to lie right down when h is about the same. So e, if you recall, is about 2.7. Thinking about 2 to the x and 3 to the x, e to the x is kind of in between those two, value-wise. Also, derivative-wise, when I had 2 to the x and small h values, the rate of change function was a little below. When I had 3 to the x, the rate of change function was a little above. When I have e to the x and small h's, the rate of change function seems to be right on top. And there are kind of more complex algebraic proofs to this, but in fact, the rate of change of function e to the x is actually e to the x. That sounds weird, like something can't be its own derivative, but that would be like saying that, I don't know, you can't have a, so the rate and the y values are just two different things. They happen to have the same values for all values of x here, which is kind of cool, but graphing a function and its derivative, I think we talked about this last time, on the same set of axes is a little odd because the y values typically are, for the two of them, are two different units. So like centimeters and cubic centimeters per minute or something. So graphing them on top of one another doesn't necessarily make sense, but just to see that they are actually the same function rule, what that means about the e to the x function and why e is a cool number, despite the fact that it's very irrational, transcendental, like pi, is that at any point on the curve, thinking about steepness sort of factors, the steepness matches up with the value of the y. So right here when y is 1, the y-intercept of e to the x, the steepness, or the slope of a tangent line, slope of a line connecting points in this little area here would be 1. When x is 1 and y is therefore e, 2.7-ish, right around here on the curve, the steepness of this is also that rate of change y to x of about 2.7 to 1. E to 1 is what that rate of change is. But the y value is growing at a rate that is exactly the same as its value for e to the x. For 2 to the x, 3 to the x, other exponential functions, the rule is, it's a fairly simple looking rule, but it's just a constant multiple times that original exponential function. The constant multiple happens to be the natural log of that number, natural log of 2 or natural log of 3 or whatever that base number is. So I'll show you the written out version of that. There, just a little bit bigger. But for any number a raised to the x power, the derivative, and I have the other notation here, that prime notation, the derivative is just a constant multiple of the original exponential function. The specific value of that constant is the natural log of the base. So the derivative of 2 to the x is 2 to the x times the natural log of 2. The derivative of e to the x can be seen as the same way. E to the x is derivative or rate of change of y with respect to x is e to the x times the natural log of e. Just the natural log of e is 1. Natural log means logarithm base e, or this ln notation is indicating a logarithm base e, the power on e that it takes to get whatever number you see afterward. So natural log of 2, quick algebra recap, natural log of 2 means what power do I have to put on the number e in order to turn it into a 2? It's going to be something slightly less than 1 because e is larger than 2. I have to make it smaller. If I want to turn an e into a 3, I have to use a number that's slightly larger than 1 as an exponent because 3 is slightly larger than e. So natural log of 2 is about 0.7. Natural log of e is about natural log of 3 is about 1.2, I think. I don't remember off the top of my head. But it's just a numerical factor out here in an actual function. Using a parameter a, we have an expression a to the x times natural log of a. And so e, if we're using e to the x, this extra factor, natural log of e, you're welcome to write that on there, but that's like putting a times 1 at the end of your statement. You don't have to write it. So the derivative of e to the x is usually just stated as plain old e to the x. All right, I'll skip that other part. So what I want to do is take a look at this lovely thing. So suppose I wanted to find the rate of change of p of x here. It looks horrifying. I have no idea what this could be useful for. But the key to looking at ugly expressions and trying to find the rate of change is realizing that most of the time you can look at small sections at a time and just strictly worry about those. Sometimes you have to look a little bit larger to see what the general structure is. I can see this 4 and then parentheses and a bunch of stuff. But looking at this, I'm like, oh, well, this 4 is a constant multiple onto all of that. I could distribute if I wanted to, but it's just a constant multiple. And constant multiples, coefficients, all I have to do is kind of carry them through to the derivative. I can just copy it down and put it in front of what the derivative would have been otherwise without it. So, oh, okay, I could think about, let me just write down this 4, and then I'll think about how do I find the derivative of what's inside these parentheses. Well, it's 2 terms. Oh, great, I know how to deal with 2 terms. I'll just do one's derivative and do the other's derivative and then add them back together again. I just have to now think about literally what are these terms. I've got an exponential function, 8 to the x, and I've got a power function, x to the negative 8. It's easy to accidentally mix up your rules for that, but just keep in mind the power rule, the subtracting one from the power, you're only going to do that if it's numerical powers. If it's a variable power, like, ooh, this is an exponential function. Exponential functions are the ones that essentially stay the same, they just get an extra constant multiple multiplied on. In this case, it'd be a natural log of 8. But just kind of look through this term by term, see if you can figure out what to do with all of these. I'll give you a few minutes to think about how do you find the derivative of all of this. The first part's kind of the messiest. How do I find the derivative or the rate of change of all of this? Just looking at a little part at a time, and we've got a few different types of rules we've learned. Alright, so this 4 is a constant multiple, or a coefficient on this expression in parentheses, so the rate of change is just going to be 4 times as much as it would be if that 4 weren't there. What's the inside? I've got 2 pieces added, so I just find their rates of change separately. What's the rate of change function, or the derivative for 8 to the x? Okay, yep, 8 to the x times natural log of 8. So 8 to the x times some positive number that I don't know what it is off the top of my head, but like close to 2. Plus. Well, I've got a derivative of x to the negative 8 that I'm supposed to be finding. This is a power function, numerical exponent. So our power rule says, well, we haven't dealt with a negative 8 power specifically yet, but it works the same as all the others, according to this. Negative 8 times x to the negative 9th. Be careful with negative exponents. It's easy to accidentally add one to the power instead of subtract one. But this power is supposed to be 1 lower than, 1 less than the original. And again, if you were like plotting this out in advance, instead of writing plus a negative, you could also write subtract. Doesn't matter one way or the other. But let's see, past the parentheses. So this is the derivative up to here, which is our first large chunk of a term. Then I've got plus, another term, minus, another term, plus, another term, minus, and minus. So I've got a bunch of other individual terms left. The next thing, though, says plus x. This is a linear function. Should have a constant rate of change. What is its constant rate? 1. The rate of change of f of x equals x. 1x is the number 1. You can also think of this, by the way, as power rule. X means the same as x to the first power. If I take a derivative of it, I can say, oh, 1x to the 0, keeping in mind that x to the 0, as long as x isn't 0, is going to be equal to 1. So this is 1. Not precisely what's going on here, but same effect. All right, so minus 2e to the x. Single term, but it's like having a negative 2 coefficient on e to the x. Well, coefficients, I can just kind of copy those down and multiply on what the derivative would be otherwise. What's the derivative of e to the x? E to the x. Easiest derivative rule ever. I like it. All right, then we've got plus x to the 10.7 power. That looks like a power term. So power rule says I'm going to do plus, let's see, 10.7 x to the 9.7. Lovely. Ooh, square root of x. It has a minus in front of it, but that's like a negative 1 coefficient. Just kind of carry it down. What's the derivative of square root of x? Yeah, 1 over 2 root x. Or you can think about it as x to the 1/2 that's being subtracted, and then write minus 1/2 x to the negative 1/2 power. But if you just like I said, square roots kind of show up a lot. If you just see it's like, ooh, square root, that's its derivative. Now what about this last term? E squared, is that a power function? Is that an exponential function? If it were on its own, well, it's e squared. It's like 8 point something. Maybe 9, I don't even know. It's a number, right? So there's no x involved in this. We're finding a derivative or a rate of change of p with respect to x. So this guy is not changing. This is like our constant function, f of x equals c. F of x equals negative e squared. If you want, you could write plus 0, especially like in your notes, maybe to indicate, oh, I didn't skip that part. The derivative of that's 0. But you don't have to write plus 0 any more than you have to write times 1. You can just leave it, but just to, I'm writing it for emphasis here, the derivative of that e squared with respect to x, since it doesn't have an x in it, it's unchanging. It's not, there's no variable, there's no variation. So 0 rate of change due to that term. Or if you wanted to think visually, if I were graphing this, whatever on earth the whole rest of it looked like, if it did or didn't have this minus e squared at the end, those constant terms that are just added and subtracted visually just shift graphs vertically up or down. This would be down by however much e squared is. It doesn't change the steepness or the location of anything else. It just, like left to right, it just shifts vertically up and down, so it doesn't affect the value of the derivative for any value of x. Questions on any of that? So that's a big, ugly function, but we actually already know how to find all of the derivatives of all of the pieces of it and put them back together. So intimidating looking bizarre expressions, if you look at them carefully, they don't actually have to be that bad. And notice we didn't do any algebra in this. We didn't do x plus h's. I didn't bother distributing here because I can just use the rules as we have them. These shortcuts are to shortcut out all the x plus h and letting h approach 0 sort of algebra that, although we can do it, it gets a little bit repetitive. So adding on to our list from earlier. So I have this kind of divided into two chunks. The top half of this are three different types of functions: a power function, a constant function, and an exponential function that we've specifically used as examples. On the bottom is about how things are connected. So far we've talked about if you have a constant that's multiplied on, a coefficient, or if you have multiple terms in a functions rule, adding and subtracting, how to deal with that. And we even saw in the last one, you can kind of combine that constant multiple with adding. We can even take care of that. Now, what we haven't talked about are other sorts of ways to combine function. Multiplication and division we're going to talk about today. And there's a variety of other sorts of functions we haven't talked about either. Now, we're going to talk about the sensibleness of some of their derivative rules. Like I said, a lot of these, I don't want to spend our class time deriving all of the rules from scratch. We'll talk about some of them now and some of them throughout the rest of the semester. But I just want to make sure that they kind of make sense. Like with the exponential, it should seem reasonable that that rate of change is, well, essentially 0 when the graph is very flat and very steep when the graph is very steep, like very high values when the graph has high steepnesses to it, visually speaking. But also just, okay, so there's kind of patterns about 2's and 3's and e's and stuff like that. We will derive some of these later, and some involves trig identities and some involve like awful weird algebra and substituting bizarre expressions for one another. But the basic function types we're going to use, besides constant functions, power functions, and exponential functions, the other ones that we'll see are logarithmic functions, either base e, natural log, or not. We're going to be using our 6 trig functions: sine, cosine, tangent, cosecant, cotangent, and, oh, secant? What did I skip? I said those in a weird order. We're also going to be using inverse trigonometric functions, where the input is the trig value, like the output from sine and cosine functions would be some weird decimals between -1 and +1. And the output to these gives you, oh, what angle had that trig value over a certain domain. There's also inverses to not just sine and cosine, but to all of the other 4. So inverse tangent, secant, cosecant. So these come up less frequently, but if you have something written where it's written as an inverse trig function, generally if you tried to rewrite it in terms of the standard trig function, it turns into a much more awful expression. So we'd like to be able to take derivatives of things from generally the form they're written in, so that we don't have to do tons of bizarre algebra to avoid it. So those are the types of functions, but besides those, we've talked about constant multiples and sums and differences of functions so that we have multiple terms. What I want to talk about now is products of functions. So if I have like 7x squared times e to the x, well, I don't really know what that is called. It's no longer an exponential function nor a power function. It's a product of the two of those. And we should be able to come up with a way to find a rate of change for it. It's not, unfortunately, as simple as dealing with sums and differences. You don't just get to take the derivatives of the factors and slap them back together. But we do get to take the derivatives of the separate factors still. We just have to put them together differently. And quotients of functions, well, multiplication and division, one can be rewritten as the other. So the rules are actually pretty similar looking, other than we end up with a quotient. And compositions of functions, we'll talk about this after break, but like for instance, if I had not a square root of x, but a square root of 4x squared minus 9x plus a natural log of 2. You know, like if I have something that I could take a derivative of, but then it has some other function performed on it, like taking a square root or raising to the 17th power or taking a natural log of it. Those compositions of functions, those are a little bit messy. Like I said, we'll talk about those after break, and we'll spend a lot of time then after break on kind of going back and forth between doing more things with these derivatives, but practice with weird combinations of things just so we get used to seeing all these different types of functions and the different ways they can be combined. And I'll have more practice questions for you. But for right now, a product of functions. I want to show you what product rule is and where it comes from, called product rule. But if I have a function that's defined as the product of two separate pieces, whether it's something like, what did I say, 7x squared times e to the x, where like either I can't multiply them together, or maybe it's just really tedious, like they're both weird polynomial expressions and I'd rather not, I can avoid having to try to write it some other way, and I'm not stuck if I can't write it some other way, because, well, let's go back to our trusty rule with the x's and h's and stuff. So if my function rule is f of x times g of x, just writing this out for not a specific function, but just for f of x times g of x, then this first half of the numerator is my f of x plus h, g of x plus h. It's this function rule evaluated at x plus h minus this function rule evaluated at x, the original rule, all over h. And then I let h become essentially 0, and we're done. But algebra simplification. Looking at this, like, well, I've got two factors in the left half of the numerator and two factors in the right half of the numerator, and none of them are the same as one another. I can't add anything, subtract anything, do anything more to multiply these. However, we can put some extra stuff in here that will actually make this easier. Adding in extra terms, which that sounds like that's totally illegal. How can I just put extra stuff in here? Well, I can put in extra stuff as long as I also take it back out. Kind of like, you know, add 1 and subtract 1, or like multiplying a fraction by the same number top and bottom makes it look different, but it's equivalent to the original. This is a trick that's used in a lot of math proofs. Let me add in these things in red. I'm going to add and subtract. Well, I actually did subtracting first and adding later. But subtracted from the numerator, f of x times g of x plus h, and then added it back in, f of x times g of x plus h. So, as I said, this is a proof technique that is used in many cases. It's a little bit similar to, it's a factoring technique that is usually in Algebra 2 grouping, where you like write in some extra terms so that you can factor something into two chunks. But in any case, if you look now at the first two terms, left to right, so the stuff in black and the first part of this red stuff, well, these two have something in common. Between those two terms, they both have a g of x plus h. If I look at the second half of the numerator now, the second red term and the original black term that was there, those two also now have something in common. They both have an f of x in them. So I've added in two extra terms that are both products. And now in the numerator, the first half and the second half are both factorable expressions, factoring out a common factor, which it looks awful right now, but if I factor out that g of x plus h from the first two terms, I have g of x plus h times, here's the leftover stuff, f of x plus h minus f of x. That sounds a little bit familiar. And then in the second half of the numerator, just keeping this plus, so factoring out a positive f of x, I'm going to be left with g of x plus h minus g of x. Also sounds a little bit familiar. So you can maybe see so far this numerator, by putting in extra terms and then factoring this out, what I'm starting to create is something where I've got an expression for the rate of change of g forming up. Rate of change of g would be that. But it's just got an extra f of x multiplied on. So maybe think about splitting this into two fractions, both of them over h. In the first one, in addition to this f of x plus h minus f of x, all over h, I've got just an extra factor of g of x plus h. And from the second half, I've got, like I said, g of x's rate of change expression, just times an extra factor of f of x. So thinking about this, not that this isn't working with specific functions, so I'm not going to be able to get rid of, like, suddenly know that, oh, this is x squared plus 2. This is just generic f of x's and g of x's. But what I have here, if I imagine h becoming essentially 0, then this expression is f's rate of change, and this is essentially g of x. So g of x times f's rate of change plus f of x times g's rate of change. So what I have here is a two-term expression for the rate of change of a function that was originally defined as two pieces called f and g that were multiplied together. So this is the derivation of this derivative rule, deriving a derivative. But if I have a function that's defined as a product, its derivative involves two products. The product of one original factor and the other derivative, and then vice versa, switch it up the other way around. The other original factor and the first one's derivative, or however you want to say that. But notice this is all multiplication and addition, so you could write this in a bunch of different orders and it still makes sense. Let me kind of clean up get the algebra out of the way here for a minute. You want to say this in words, the rate of change of a product of functions is the first times the rate of change of the second plus the second times the rate of change of the first. Or, in other words, if we're dealing with something like, I'm going to try to remember what I said earlier. I'll call this function q of x. I'm not going to call it f. So what did I say? 7x squared times e to the x. And you might not see a times sign written there. I'm just writing it kind of for emphasis. I can't combine these anymore. It's not a power function. It's not an exponential function. It has one factor of each type. So if I want to refer to this as the f of x from above, and think of the second part as the g of x, then according to our product rule here, the derivative or rate of change of function q, this product with respect to x, is going to involve, well, kind of whatever order I want. F times g prime and g times f prime added together, or, and I think the previous slide said g times f prime first. Like I said, doesn't really matter, but I know how to find the derivative of this part on its own. It's a coefficient on a power of x, so I'd have 7 times 2x to the first, otherwise known as 14x, times the original, so this is f prime of x, times the original other factor, g of x, e to the x, plus, other way around, the original first factor, 7x squared, times g's derivative. What's the derivative of e to the x? E to the x. So it doesn't look like we took the derivative of it, but we did. This is the derivative of this specific product. If I had something like, let's see, w of x equals 19 to the x times the square root of x. I could find the derivative of that using product rule, because I know how to find the derivative of an exponential function, and I know how to find the derivative of power function or square root function. W's derivative with respect to x would have the derivative of 19 to the x, 19 to the x, natural log of 19, times the original square root of x, plus, other way around, the original 19 to the x, and the derivative of square root of x. Now, one thing I want to point out, both of these rules, there are ways you could, like, there's common terms between them, you could factor and write it some whole other way. Don't worry about that. What I'm concerned about, both for the purposes of your homework and your mastery test, is can you do the calculus? I don't want you to try to make your answers look pretty. Please don't spend time and energy on that. If you want to, if it makes you happy, go for it. In terms of, like, if you're looking at solutions from some example problems you found online, you might see something like this done at the end of this. It's like, let's see, so I can take out a factor of 7 and an x and an e to the x. So 7x e to the x times 2 plus x. And if you just saw that, like, what on earth did they do? Oh, well, they just did the regular product rule, but then they did extra algebra afterwards, which hides what was done. So when you see sometimes these simplified answers, it's a little bit hard to figure out what happened. Like, where did 2 plus x come from? I don't see 2 plus x anywhere in there. That's just the leftover pieces from factoring. So just, like I said, don't be concerned about doing factoring like that. But if you are like looking online for extra problems and checking yourself or something, you will see that done sometimes. Answer keys like to have things succinct, but don't worry about doing that in terms of it's not wrong to not do that, or it's not better to do. It's just alternate ways to write it. And when you don't do that, I can see what all of your work is, essentially. All right, so quotient rule actually involves a lot of the same steps. I'm just going to cut to the end of it and kind of point out. Do I have it here? Yeah. Quotient rule is for if I have a division between two functions. And typically it's written as a fraction, so it kind of stands out easily. But just to show like what is this rule? It comes from thinking about product rule with a -1 exponent. There's this part in the middle that is related to what's called chain rule or composition of functions. But the end result is, for a quotient of two functions, the rule for finding the derivative is very similar to a product of two functions. It's a quotient, but look at the numerator here. In the numerator, I've got, for my original function with the function f on the top and a function g rule on the bottom, I've got f and g, one derivative, one original, and then minus the other way around. That's kind of like product rule, but with a subtraction in the middle, which does mean the order is important, unfortunately. And a denominator of, well, whatever the original denominator was squared. We'll talk about more of the details of what all is going on here after break, but the usage of this is not that bad. Oh, oops, and this is not the page I wanted. Let me just open up a GC page. So quotient rule, typically the way it's written is something like, if I have, let me just rewrite this. So I had, I'll just call it q of x. If q is one function over another function, f is the numerator, g is the denominator, then q prime, its derivative, involves the derivative of the numerator times the original denominator minus, other way around, and you can write the products in whatever order you want. Like I could write g first or f prime first, but the subtraction does give us a particular order, where the numerator's derivatives in the first part, the denominator's derivatives in the second part. And I've got this fraction by the time I'm done. So if I have something like q of x equals 4x plus 2 over 2 to the x. Let me not use 2. There's too many 2's in there. 3 to the x. As long as I can find the derivative of the numerator and find the derivative of the denominator, all it is just putting these in place. I have the derivative of the numerator times the original denominator, 4 times 3 to the x, minus, other way around, 4x plus 2 times 3 to the x times the natural log of 3, all over the original denominator, squared. And other than, I'm going to make my fraction line look a little longer. There we go. Don't worry about what your answer looks like. Like, oh, I should simplify something or square that out. Don't worry about it. Just get the calculus done, and we can talk about simplifying if you want to, but that's not the important part. The important part is I want you to see how the pieces go together in these rules, and then we're going to use some more rules. So as for over break, make sure that you look through, there are more examples in this section 6.3 here in your book, and there are a bunch of IMath AS practice derivatives and assignments, like was it 10 11, 11 and 12. They start out easier and then they get harder as they go on. There are other individual function rules. We'll talk about logarithms and trig stuff, but once you kind of know how these work, just look at those rules. We'll talk about some of them. You'll talk about some of them in recitation, I'm sure, and I will see you after break.